AI is being sold as software, a chat window, a model, a promise that intelligence can be called up on demand. But under that promise sits something much less abstract. Memory chips, packaging lines, silicon interconnects, substrates, and factories concentrated in a handful of Asian manufacturing clusters. The economics of the AI build-out are not being decided only by model design. They're being shaped by a physical supply chain that is capital-intensive, capacity-constrained, and exposed to real-world disruption. This episode is about that gap, and whether the story of abundant intelligence can hold if the hardware chain does not cooperate. Start with the demand-side framework. OpenAI has described a thesis around building abundant intelligence, and the logic is straightforward. If the marginal cost of intelligence falls, AI becomes available to more users and more enterprises. That broader adoption supports more infrastructure spending, which should then help drive costs lower again. In theory, it is a reinforcing cycle. But the framework is mostly economic, not industrial. It does not rest on a list of factories, packaging lines, or memory suppliers. That omission matters because the entire loop depends on hardware becoming cheaper and more available over time. If the physical inputs to AI remain scarce, delayed, or concentrated, then the cost curve does not simply glide downward. It stalls, bends, or rises. The first pressure point appears in memory. Samsung's second quarter earnings call offered a warning that reaches well beyond one company's outlook. Executives said global memory shortages are expected to worsen in 2027 and persist through 2028, driven by AI demand. That matters because AI infrastructure is not defined only by the processors that attract most of the attention. Training and running large models also depends on large volumes of high-bandwidth memory and related components that work alongside the main compute chips. If memory remains tight, then the cost of building and operating AI systems may not ease on schedule. It may stay elevated. And this is not only a hyperscaler issue. Tight memory supply has historically had effects that spread into consumer electronics pricing as well. So the first challenge to the abundant intelligence thesis is basic but important. One of the key inputs needed for scale may be getting scarcer rather than cheaper, at least for the next several years. The next constraint sits deeper in the supply chain, in a layer that rarely gets broad public attention: packaging and testing. This is where ASE becomes important. Taiwan's leading back-end semiconductor company has raised its 2026 capital expenditure guidance to $10.5 billion, marking its third upward revision this year. That is a notable signal on its own. It becomes more significant when paired with the company's reported 35% year-over-year growth in AI-related packaging and testing revenue in the first half of the year. The core point is easy to miss if AI is viewed mainly through chip design or wafer fabrication. A chip is not commercially useful at scale just because it has been manufactured. It still has to be packaged, tested, qualified, and delivered in volume. That back-end process is where design becomes a deployable product. ASE's repeated capex increases suggest that this layer of the chain is under real pressure from AI demand. In other words, one of the practical limits on falling AI hardware costs may not be at the front end of semiconductor production, but in the back-end capacity needed to turn finished dies into shippable systems. That packaging story becomes more revealing when the competitive landscape is examined, especially the gap between announced alternatives and actual production readiness. This is where Unimicron's disclosure about Intel matters. Unimicron has indicated that Intel's EMIB-T advanced packaging platform will not reach true mass production until 2027. That timing is significant because EMIB-T has been presented as a possible alternative to TSMC's CoWoS technology, which currently dominates high-end AI chip packaging. The issue here is not whether alternatives can emerge. It is whether they can emerge fast enough to change the near-term balance of capacity. A platform that is not yet in true mass production cannot meaningfully absorb demand away from an established incumbent. That suggests dependence on TSMC-centered, Taiwan-based advanced packaging is likely to continue longer than some diversification narratives imply. For investors and companies looking for near-term reduction in concentration risk, The message is not that diversification is impossible. It is that the timeline may be longer than expected. The response to these pressures is also spreading into adjacent parts of the hardware stack, and UMC offers a useful example. The company has outlined a planned $5 billion investment over 2 to 3 years into silicon photonics and advanced packaging, alongside an increased 2026 capex budget of $2 billion. This matters because the AI bottleneck is not only about compute density. As systems scale, the ability to move data efficiently between chips and between servers becomes increasingly important. Silicon photonics addresses that challenge by using light-based interconnects that can reduce energy loss at these scales, compared with traditional electrical connections. UMC's spending plan suggests that value in the AI supply chain is not confined to the most advanced logic nodes. It is also accumulating in packaging, interconnect, and system-level integration. That broadens the investment map. At the same time, it does not loosen the regional pattern. The investment still points back to the same Asia-centered manufacturing cluster, tied here to Taiwan and Singapore. That concentration is what makes the final piece of this story so important. A 7.1 magnitude earthquake struck Kumamoto Prefecture in Japan, with a reported death toll of 34. The human cost comes first. But for the AI hardware chain, the industrial implications also matter. The quake reportedly led facilities tied to Renesas, Sony, and Tokyo Electron to suspend operations. These are not peripheral names in electronics and semiconductor production. The broader lesson is not about forecasting the specific impact on one company. It is about geography and resilience. As Asia adds more strategic manufacturing capacity to support AI demand, that capacity remains clustered in locations with real exposure to natural disaster risk. Restart schedules, damage assessments, and downstream logistics effects remain open questions. And those questions matter because so much of the physical AI stack depends on a limited number of regional nodes functioning without interruption. Taken together, these signals do not support a simple bullish or bearish reading. OpenAI's vision of abundant intelligence may still hold over time, but only if the supply chain beneath it becomes more capable, more efficient, and more resilient at once. Samsung points to memory tightening rather than easing. ASE points to back-end capacity expanding under strain. Unimicron's disclosure suggests alternatives to Taiwan's packaging dominance are arriving more slowly than some had hoped. UMC shows capital being redirected into interconnect and packaging layers that are becoming strategically central. And Kumamoto is a reminder that even highly sophisticated manufacturing clusters remain exposed to disruptions no roadmap can eliminate. For investors, the practical takeaway is to focus less on rhetoric and more on the hard indicators that sit under the AI narrative. Watch memory supplier commentary and pricing signals to see whether Samsung's 2027 and 2028 shortage warning begins to firm or soften. Watch ASE's packaging and testing trajectory for evidence of sustained demand or signs that expansion is catching up. Watch whether TSMC's CoWoS dominance is meaningfully challenged before Intel's EMIB-T reaches actual volume production. Watch whether UMC's capex turns into visible traction in photonics and advanced packaging. And watch how quickly Kumamoto-linked operations recover, because recovery speed is itself a test of regional resilience. The important shift is that AI exposure in Asia now extends well beyond leading-edge logic. It runs through memory, packaging, interconnects, and the surrounding industrial capacity needed to scale systems in the real world. But the risk profile expands with it. More capital intensity, more bottlenecks, more technology readiness gaps, and more geographic concentration. The marginal cost of intelligence may still decline over time. Whether it declines on schedule will depend less on the next model release than on whether Asia's physical supply chain can keep pace with the ambition built on top of it.